Let's look at another way to calculate definite integrals. Now, this really only works for special cases where the integral is for a function that closely relates to a geometric shape. For example, the function that we're looking at here is the square root of 9 minus x minus 3 squared. And this is actually a semicircle. If I replaced f of x with y, and then we did a little bit of algebra here, we could square both sides. That would become y squared equals 9 minus x minus 3 squared. And if I moved this term to the other side by adding it, it would look like x minus 3 squared plus y squared equals 9. And this is a circle that is centered at the point 3, 0, and it has a radius of 3. So knowing that, we know we're looking at a portion of a circle. And so if we're going to calculate the area, we're going to look at the formula for area of a circle. Area of a circle, hopefully we remember, it's pi times radius squared. Now we know the entire circle area would be pi times 3 squared, or 9 pi. However, we're not looking at the entire circle, we're just looking at the portion of the circle from 3 to 6. Now thinking about the fact that this circle is centered at 3, 0, so if we were to try and graph that, then we know the center is right here, and the radius is 3, so the circle looks, the full circle, ooh, whoa, would look something like this. But we're not really considering the full circle. Remember that our function was written in the form positive square root, which means we're only considering the top half of the circle. And we know that the center of that circle was at 3, 0. And we're going to consider all the way up to the end of the circle because our interval was from 3 to 6. So if a radius is 3, then we know the end of the circle would be at 6. So if we're looking at the area underneath that curve from 3 to 6, then we're really not considering an area of a full circle, we're considering a quarter of a full circle. So the area that we're going to use would be the 1/4, the area of a circle with radius equal to 3. So we're going to do 1/4 times pi r squared, where r is 3. So our final answer would look like 9/4 times pi. And that would be the area, the exact area under the curve between the bounds x equals 3 and x equals 6. Let's do one more example from section 5.2. This is example 5.9, and it's talking about finding the net signed area. Now, what happens is sometimes we talk about area under a curve, and we consider functions that go below the x-axis. So this function, 2x, if I were to graph it, it's a line, goes right through the origin. When x equals 0, y equals 0, and when x equals 1, y equals 2. So I know my function looks something like this, more of a straight line than what I've got, but we'll deal with it. And we're looking at the interval from -3, so I would need my function to extend quite a bit, to +3. So let's pretend -3 is here and +3 is here. We're looking at this area and this area. Area that's below the x-axis is called negative area. Now, we know that negative area is not quite a real thing, but we do interpret it this way when it's below the x-axis. We call it signed area. So rather than interpreting it as negative area, we would say it's a signed area. So the area below the x-axis is negative. And area above the x-axis would be positive. Now, for us to integrate this function, 2x, over the interval from -3 to 3, we could write that as so. And if we wanted to, we could interpret this as two separate triangles. So the positive area looks like a triangle with a base of 3 and a height of, well, we need to take that 3, plug it into our function to find our height. So that's going to look like 6. 2 times 3 is 6. So from 0 to 3, we have one triangle, and from -3 to 0, we have another. So let's separate our integrals. From -3 to 0, and then from 0 to +3. Because that first integral is going to give us our negative area, and the second integral will give us our positive area. And each one of these can be represented by a triangle. This negative area has a base of 3 and a height that goes down to -6. And then the positive area has a base of 3 and a height that goes up to +6. And so we can do our negative area, base area of a triangle. Hopefully we remember that. It's 1/2 base times height. So 1/2 -6 times 3. And then for the second triangle, it would be 1/2 +6 times 3. In other words, we have -9 plus +9, which is 0. So this is something to think about. If you have a function that dips below the x-axis and you are looking for net signed area, the negative area or the area below the x-axis is going to balance out with the positive area. Sometimes it'll equal out to 0, but not always. If we had shifted our interval a little bit to where there was less area below the x-axis and more area above the x-axis, this would not have worked out to be 0. But with the symmetry of this function, the final result was 0.